The biggest shift here is that training for reasoning is finally being treated like reasoning itself. Sequential, fragile, and highly sensitive to where the model almost got it right. That matters because the current bottleneck isn't just accuracy, it's stability, calibration, and whether the model can keep learning without collapsing into safe, repetitive behavior. Across these papers, a clear pattern emerges. Better test time scaling, better RL dynamics, and more honest personalization all depend on finer-grained signals than today's coarse training loops usually use. Keep watching, because the details show exactly where current LLM training is fooling us and how researchers are starting to fix it. Let's explore the first paper, Revise, Revision, and Verification, 205 Augmented Training for Test Time Scaling. Reeves, from Northwestern University, Amazon AGI, Qualcomm AI Research, and the University of Minnesota, reframes test time scaling as a meta-RL problem and targets sequential revision rather than single-shot accuracy. The key idea is that standard RLHF-style post-training is misaligned with multi-step inference, so the method decomposes sequential revision success into per-state, one-step recovery probabilities and trains on near-miss intermediate answers by converting them into separate revision and verification prompts. This two-stage loop alternates between offline data augmentation from successful revision trajectories and single-turn RL updates, avoiding the credit assignment noise and long-horizon sampling costs of multi-turn RL. On Live Code Bench, Reeves improves over the RL baseline by 6.5 points and over standard multi-turn training by 4 points. On circle packing, a Quen 3-4B model reaches the previously reported optimum sum of radii 2.635983 at n equals 26, matching much larger evolutionary search systems including Gemini 2, Zero Pro, Flash, and Quen 3, 8B. For math, it substantially boosts sequential revision accuracy on AMI 2.4, AMI 2.5, and Math 5.0.0 under Oracle and self-confidence stopping, and the learn policy transfers to other revision using test time algorithms such as MCTS, ABMCTS, and mind evolution. The paper also reports that continual augmentation matters. One-time augmentation underperforms epoch-by-epoch regeneration, and verification prompts improve calibration, raising AUROC on AIM 2.5 from 72.1% to 74.1%, while revision prompts primarily drive recovery performance. Let's explore the second paper, Recentering Humans in LLM Personalization. Recentering Humans in LLM Personalization, from the University of Illinois Urbana-Champaign and Carnegie Mellon University, argues that synthetic personas and LLM judges systematically overstate how well models personalize for real people. The paper decomposes personalization into 3 stages: extracting stable user attributes from conversation history, matching those attributes to a new prompt, and generating a response that beats a generic baseline. Using 550 real conversations from WildChat and 5,949 attribute validity judgments, 11,919 attribute prompt relevance judgments, and 1,101 response preference judgments, the authors show that real conversations are harder than synthetic data. Extracted attributes from human dialogue contain many more uncertain or rejected cases, with overgeneralization accounting for 53.9% of failures. In relevance matching, humans mark only about 20% of attributes as relevant, while LLM judges mark 40-60%, with average human LLM agreement dropping to kappa is approximately equal to 0.3. Lightweight interventions help. A trained Roberta verifier reaches 0.726 F1 for attribute verification, and a Quen 3.4B model optimized with GRPO reaches 0.641 F1 for relevance selection. But the third stage remains difficult. Humans judge 54.6% of personalized responses as no better than generic, and LLM judges show only modest alignment with human ratings, with Spearman correlation peaking around 0.376. The core message is that personalization quality must be grounded in human judgments, not just synthetic benchmarks or surface-level attribute mentions. Let's explore the third paper, Stare Surprisal Guided Token Level Advantage Reweighting for Policy Entropy Stability. Stare, from Tsinghua University and Tencent Hunyue, targets a specific failure mode of GRPO-style reinforcement learning with verifiable rewards. Policy entropy collapse that prematurely ends long-horizon training in large language models such as Quen 2, 5, Quen 3, and DeepSeek Air-in variants. The paper's core technical result is a first-order entropy analysis showing a token-level advantage surprisal 4-quadrant structure where entropy change decomposes into the product of trajectory advantage and a local surprisal sensitive term. This reveals that shared trajectory level advantages systematically over-reinforce low surprisal majority tokens while underweighting the high surprisal minority that preserves exploration. Stare operationalizes this insight by selecting entropy-critical tokens via batch internal top P% surprisal quantiles, reweighting their effective advantages inside the clipped GRPO surrogate, and using a closed-loop target entropy gate at HTGD equals 0.3 to turn intervention on only when batch entropy falls below target. Across models from 1, 5B to 32B, the method sustains stable RL for thousands of steps, including over 5K steps on 7B and over 5K steps on 14B and 32B, while maintaining entropy within the target band. On AIM-2.4 and AIM-2.5, Stare outperforms DAPO and other baselines by 4%, 8% in average accuracy, with the strongest reported single-setting gains reaching 54.4%, 66.3%, and 60.4% average accuracy in the short COT, long COT, and tool use regimes, respectively. Ablations show that fixed W equals 1.1, P equals 10%, and batch level gating are the most robust defaults. That's a wrap on today's AI paper highlights. Thanks for watching.